Hey everyone! Today we are diving into the world of chemistry to uncover the secrets of a little wonder drug you probably have in your medicine cabinet aspirin. Yep, that tiny tablet that saves your headache and keeps your heart happy. But have you ever wondered what's inside and how we know what aspirin really is? We will explore what it is, how it works, how we can see its structure using chemical analysis, and why it's used. Let's begin. Chemical identity and structure. Aspirin's chemical formula is C9H8O4. Its IUPAC name is 2-acetoxybenzoic acid, or orthoacetoxybenzoic acid, and its systematic name is 2-acetyloxybenzoic acid. If we look at its molecular structure, aspirin contains a benzene ring, a carboxylic acid group, COOH, an ester group, OCOCH3, formed by the acetylation of the phenolic OH of salicylic acid. So its main functional groups are aromatic ring, carboxylic acid, and ester. This combination gives the molecule its distinctive chemical and pharmacological properties. Drug classification and mechanism of action. Aspirin belongs to the class of nonsteroidal anti-inflammatory drugs, or NSAIDs. Its mechanism of action is quite well established. Aspirin irreversibly inhibits the enzyme cyclooxygenase, or COX, both the COX-1 and COX-2 isoforms. Specifically, the acetyl group of aspirin attaches or acetylates a serine residue in the active site of COX, blocking the enzyme's ability to form prostaglandins and thromboxanes. As a result, production of prostaglandins, which mediate inflammation, pain, and fever, is reduced, giving aspirin its anti-inflammatory, analgesic, and antipyretic effects. Production of thromboxane A2 in platelets is inhibited, which reduces platelet aggregation or clot formation, giving aspirin an antithrombotic or anticoagulant effect. Because the inhibition is irreversible, the effect on platelets lasts for the lifespan of the platelet, which is about 7 to 10 days. This dual action, reducing pain or inflammation and preventing clotting, makes aspirin useful in many conditions. Therapeutic uses. Aspirin is used for relief of mild to moderate pain such as headaches, muscle aches, dental pain, etc. Reducing fever or antipyretic effect, reducing inflammation in conditions like arthritis or other inflammatory disorders. It also works as a cardioprotective agent. In low doses, aspirin helps prevent heart attacks, strokes, and other thromboembolic events due to its antiplatelet action. Spectroscopy. When chemists need to confirm the identity of aspirin or ensure its purity, they use spectral analysis methods. Let's briefly review three of them. IR spectroscopy. Let's analyze the IR spectrum of aspirin. Around 3,200 to 3,400 per centimeter, we see a broad peak, which is characteristic of an OH stretch, indicating the presence of a carboxylic acid group. Next, at 1,750 per centimeter, there is a strong, sharp peak. This corresponds to the C-double bond O stretch of the ester group in the acetyl part of aspirin. Moving to 1,680 per centimeter, there is another sharp peak, which represents the C-double bond O stretch of the carboxylic acid group. At 1,600 per centimeter and 1,500 per centimeter, we observe medium peaks, which are due to aromatic C-double bond C stretching vibrations, confirming the benzene ring is aspirin. Around 1,000 to 1,250 per centimeter, there are sharp, intense peaks due to CO stretching vibrations from both ester and acid functional groups. Lastly, the peaks below 900 per centimeter correspond to aromatic CH bending vibrations. Proton NMR spectroscopy. Let's break down the proton NMR spectrum of aspirin. First, at 2.1 ppm, we see a singlet representing 3 hydrogen atoms. This comes from the methyl group in the acetyl part of aspirin. Since it has no neighboring hydrogens, it appears as a single peak. Next, we have 4 peaks between 7.4 and 8 ppm, each corresponding to 1 hydrogen atom on the benzene ring. These peaks show a splitting pattern called DDD, which stands for doublet of doublets. It means that each hydrogen is being influenced by 3 neighboring hydrogens, each causing a slight shift. This tells us that these hydrogens exist in a complex environment, which is typical for aromatic hydrogens in a substituted ring like in aspirin. Carbon-13 NMR spectroscopy. Now let's look at the carbon-13 NMR spectrum of aspirin. Starting with the methyl group, we see a peak at around 20.6 ppm. This is typical for a CH3 group attached to a carbonyl. Next, we have several peaks between 122 and 135 ppm. These correspond to the aromatic ring carbons, each one in a slightly different chemical environment due to substitution. We also observe a peak at 151.2 ppm, likely representing the quaternary carbon in the aromatic ring connected to the ester or acid group. Finally, 2 strong downfield signals appear at 170.2 ppm and 169.6 ppm. These are the carbonyl carbons of the ester and carboxylic acid groups, both highly deshielded due to the oxygen atoms attached. Mass spectroscopy. Now let's take a look at the mass spectrum of aspirin. The tallest peak, also called the base peak, appears at mass over charge 120, meaning it's the most abundant and stable fragment formed during ionization. At m over z 138, we see another strong peak, which is a significant fragment, possibly from the loss of a CH3 group or rearrangement. The molecular ion peak is expected around m over z 180, which corresponds to the entire aspirin molecule, but it appears here as a very small peak. We also observe other smaller peaks, such as at m over z 43, m over z 92, and m over z 65, which are due to smaller fragments of the molecule. These fragment peaks help confirm the structure of aspirin by showing how it breaks down in the mass spectrometer.